Welcome to Pavilion Data's webinar, Simplify Data Center Operations and Reduce Costs with Rack-Scale Flash. My name is Brandon Graff, Head of Marketing here at Pavilion. Today's speaker is VR Satish, Founder and Chief Technology Officer of Pavilion Data. VR has over 20 years of experience in the storage industry, including serving in executive leadership roles at Veritas and Symantec. We encourage you to submit questions via the webinar interface throughout today's session, and VR will answer as many questions as possible. With that, VR, I turn it over to you.
Good morning, everybody. Today I'm going to be talking about Rack-Scale Flash. What are the advantages, how to use them, and why somebody would want to do this. I'm assuming that everybody can hear me right now. If not, do send a chat out to say that you can or you cannot hear them. First things first, I'll start off by level setting what the reality is. As we all know, budgets are flat. The number of employees in the data center or operations are constantly coming down. The amount of storage is growing unbounded. The amount of hosts are increasing because we just need to do more. The need for better performance and uptime and reliability is also going up. I'm sure that everybody is feeling this pain. So how are people really trying to address this? Well, there are a few knobs which people generally try to tune. And obviously this is not a full set. There are more, but these are the main three knobs. A, work on operational efficiency. One can try to move with IT as a service through automation, set up self-service portals, private clouds, so that consumers can consume infrastructure on demand. Simplify offerings in architecture, just go standardization, so that the lesser the number of tools an organization has to deal with, the easier it is, and the lesser the staff that you need to deal with it, the training and all that. And there's also the new hyperconverged initiative, where it's all in a box. It's IT. I would say it's a cloud in a box kind of situation, where it's very simple to operate, add, provision. So operational efficiency is definitely one knob which you can try to tune. The second one is lowering cost. Obviously people are at a crossroads right now where they want to move to the cloud completely, and a bunch of question marks around there. The sense is cloud is all about, in my opinion, about spin down economics. So essentially, if you are running an application in a bursty fashion, for example, less than, let's say, 15 days a month, I think that you should go to the cloud. I mean, the benefits are profound. But if you're going to be running it 24/7, greater than 15 days, if I may, then people are realizing that it's better off just moving it in-house. The other way of lowering cost, obviously, is white box everything. Go to an ODM, buy the servers from there, build your own storage kind of stuff, software defined everything, and throw out proprietary software and go with open source as much as possible. There are people who are moving from Oracle to MySQL. This is another cost saving mechanism. They have their advantages, they have their disadvantages. And from a performance point of view, this is a need. And obviously, the more the performance you want, it's going to cost a little bit more money. It's not always going to go down. Faster CPUs are required, faster networks are required. People are trying, because of the amount of data that is out there, what we call the data deluge. People are just saying, and you have to analyze and manage all this data. Performance is key. So people are saying, move the data over closer to the CPU so that you can get better access. So this has spawned the whole server-side storage, DAS, along with operational efficiency that you get out of that. And scale up. Instead of buying monolithic storage arrays as we knew it, or know it, people are more and more inclining towards scale out so that expand on demand as the data keeps going larger and larger. You know, this is a conundrum, and one of the issues that all these three knobs are such that you tune more on one knob, the other one gets impacted. You tune the other one, the third one gets impacted. So to get all three of them is a very difficult challenge that people have today. I'll give you a simple example here around simplification versus wastage. You know, there's a tug of war. The more the simplification you do in certain areas, the more the wastage that happens. To give you one particular example, one of the way people try to simplify their operations is through standardization. This means, you know, without standardization, procurement becomes very complex. For example, you know, you want to dole out resources for an application. You know, the application's needs are very different from one another. How many cores do they need? How much memory do they need? How many servers do they need? What kind of storage do they need? How much storage do they need? There are too many variables here. If you're trying to get it right fit for every application, there's what becomes a SKU explosion. Your procurement becomes a complete nightmare. So people try to simplify this. There are lots of initiatives in many operational data center operations, IT organizations, where they say, look, we're going to standardize this stuff, and we're going to just give 3 simple offerings. 3 maybe a little too less, maybe 5, maybe 6, rather than having indefinite amount. For example, we're just going to do large, medium, and small. If you look at the figure on the right, you know, sometimes applications require lots of CPU and lots of memory, but not that much storage. When you have combinations of just large, medium, and small, just simplified to the degree, what happens is it costs wastage in storage. Now, if somebody requires lots of storage, but doesn't use a whole lot of CPU and doesn't need a whole lot of memory, then you're starting to waste CPU and memory. So here's a simple example where a process of SKU simplification has resulted in wastage of resources. So what's the solution to this stuff? You know, there's a new trend. People are talking still in the research labs, if I may use, everything composable. In essence, kind of think about it like software-defined servers itself, where people are trying to say, look, nobody ever deploys a server at a time in a large data center. People deploy a rack at a time, and they don't want to manage at the granularity of the server, but they want to manage at the granularity of the rack. So the rack is a real procurement system, entity that you procure, and it's got everything. So if you really want to slice and dice this stuff, I mean, you can pool memory, you can pool CPU, you can pool storage, and assuming you have an extremely fast interconnect, so fast that it can even, you know, link CPUs together and memory together and storage together, then you can do what virtualization did to physical servers, essentially take a whole rack and slice and dice it up to the requirements of the application and dole it out with absolutely no performance benefit, no performance degradation. It's as good as, you know, getting bare metal servers right sized for you, which the application needs. Now, there's also another fundamental thing you have to look at when you're going over to more rack scale design or composable everything. Now, today, the way procurement works is it starts with the application. So you define what are the needs of the application, and then you know, put out an RFI for it, and you get, you know, vendors who are going to actually try to satisfy that. And then you go and do a POC and procure and all sorts of things there. Now, when you go to a standardized rack scale design, this is not a scalable model, because to just get an application off the ground takes, you know, a lot of time. This is what we solve with virtualization, and to a certain degree. The behavioral change that is required is more around how an infrastructure can adapt to the needs of the application, which is, you know, all in line with the composable everything. So you define a standardized architecture and standardized procurement. A rack is a unit of management. Just buy racks and hook them up together, and you slice and dice it based on the needs of the application. So it's more infrastructure at the forefront, procure first, and then it'll adapt to whatever the needs of the applications are, rather than the other way. But however, as I said, a lot of this stuff is still in research. The disaggregate everything, because the CPU link or memory link requires technology such as cache coherency management and all sorts of things. However, there's one area where we can disaggregate today. Technology exists, and the easiest thing to disaggregate right now is storage. So when you look at a scale out server storage kind of model, combined hyperconverged model, you can actually take the storage from inside the server out and consolidate it at the rack level, with absolutely giving no loss of performance whatsoever, but getting the benefits of shared storage, which goes a very long way. So what are the new technologies that are here? So we know that there's an initiative called NVMe Express over Fabric, NVMe over Fabrics. This basically allows you to almost give in-server performance for storage, even though it has been disaggregated to outside the confines of the server boundary. In addition to that, there's this new technology called storage class memory, be it faster NAND flash with better technology, or the Intel's later Optane drives kind of stuff. The whole game is changing with respect to storage, because we need to process more data, more parallelism, and more answers to questions in pretty much real time. So why do we need to disaggregate storage? Let's just take another step back and say, we said we need to disaggregate everything. We saw some benefits. Then we also said we have the technology that is required, that is needed to disaggregate storage, that is readily available. And let's take a little deeper look at what benefits do we get when we disaggregate storage. If you look at server-side storage today, because of the need for availability and reliability, you are required to make multiple copies or multi-copy mirroring across servers. Typically, people do 2 copies in addition to the original. That was okay for disks, because disks were relatively cheap. But when you're looking at, performance needs too, 1/3 of the usable capacity just goes out the window. Right there. The second one is locality of data. It can so happen that the data doesn't fit inside one server. So it has to stretch out to the adjacent servers, and you really have to do efficient cache management, or you're going to go on the network to go fetch the data, which kind of defeats the purpose of having data within the server. The third more important stuff is predictable performance. The reason we went to server-side storage were 2 things. One was the need for speed. The second one is agility. Now, if you take the intersection where you need the speed as well as you need the agility, who doesn't? You're going to find out that in this kind of an environment, you're going to have very unpredictable performance. Why? As applications, which are designed in business unit as a project, become successful and people like it, it transitions over to the IT department. And as it transitions over to the IT department, the process of IT department is to make sure that backups are taken, make sure the data are ETL properly, the servers are compliance scanned, security checks, all sorts of these scans keep going on happening. And how many of you have seen the problem where when there's an antivirus scan going on your laptop, pretty much becomes unusable? So something similar happens here when you have a backup going on. So if you look at a server-side storage, when a backup is happening, what happens is it directly impacts the application's performance, because it starts using CPU memory resources and generates a lot of I/O and contends with the I/O of the application in itself. So the fundamental premise on moving to this for high performance, making storage closer to CPU, kind of breaks down when you have to do any of real, enterprise-related, jobs. When you look at a macroscopic level. So all these issues that help popularize SAN really exist even today. So we see that history kind of repeats itself. So none of these problems existed 25 years ago, where we had servers inside storage, a storage inside server like hard drives in server. Then we saw hey, this is not going to really work. There's not enough slots out there. Let's move the storage outside. We created server side. We created JBots, and we started accessing them through multi-initiated SCSI and all that stuff. Then somebody had a bright idea and said, look, let me virtualize the storage those are in these JBots, and created Volume Edge. And each of these, by the way, created multi-billion-dollar companies. I mean, this was the need of the hour at that time. And then yet another set of companies came and said, why would you use the resources of the server? Let me virtualize everything inside what I call now a storage array. This is what EMCs and NetApps and all these guys were born, right? Now you see for the new age applications where data is so much that people are going towards server SAN, and the need for speed has caused NVMe drives or Fusion IO cards or whatever the equivalent is today, in these servers. These problems just haven't gone away. So we see a new breed of companies getting formed with saying, let me take these drives out and create JBoss, to serve this. And then there's a set of companies which come out and say, I'll virtualize this. I add data management services, and they create the equivalent of a volume manager running on the servers, kind of virtualizing the JBoss and creating a solution. And then there's a company like ours, which is Pavilion Data, which just looked ahead a little bit and said, look, these things having agents on every server is a real problem in large-scale data centers. So we're going to take this over and not use any resources on the server and do everything inside the box itself. So this is, a job of a CTO, if I may say, is actually very simple in this world. They just look back, and history keeps repeating itself, and these problems don't go away. Now that we said, well, let's go back to sharing, but then we start scratching our head and saying, can we share but remove the operational complexity that was there in SANs? And I believe it's completely possible. So let's look at rack scale flash. When I say sharing, it doesn't mean that you have a complete network for just all storage together, and then there's server far away, and you cable them through, large scale SANs and share all across the board. No, you share to a certain degree. You don't share like how you want to, what you did with SANs. What if you could just say, look, I'm going to share it at the rack level. Disaggregate the storage that was inside the servers, move it at the bottom of the rack or at the top of the rack along with the switch, and what would happen? So immediate benefits are very simple in the sense you get 2x better storage utilization. Why? You don't need to make the 3 copies anymore. Right? That was one thing. The second thing is, remember I talked about the SKU consolidation costing wastage? That goes away because you can provision the application on demand when the application is provisioned. And this kind of a late binding allows you to, better utilize your resources. At the end of the day, pooling has benefits, and that's one of the reasons why we see some benefits of economics in the cloud. Now that you have taken a lot of the data management services, which you would typically run on the servers, down into the bottom of the rack flash intelligence system, you tend to improve your performance 100%, straight up there. There's zero contention of the CPU, memory, storage software, none of this runs there. And the CPU, memory, everything is dedicated for running its primary purpose, which is the applications. In addition, you get operational efficiencies. You could just take snapshots if the system provides a snapshot, and you could store them for 30 days, just like we did in the good old days. And you could do off-hosted backups, and you could do off-hosted ETL, you could do off-hosted compliance scans, security scans, all that benefit without having any of these data management windows for the application. Now your application gets dedicated 24/7 resources that it can count on and work fast. Let me go a little bit more into why is this a challenge? It looks so simple. Why are we doing this? Why are we not doing this? One of the big factors is if you look at the storage systems that are there today, they're designed for the disk era, rotating media, mechanical devices. Let's take a typical example of an NVMe drive specification. You would see that they can really perform very high. If you look at this sample one, random reads can go anywhere like 800 IOPS plus, and random writes can, up to 200,000. That's phenomenal. But the thing here is, the CPU interconnects with these devices using what we call PCIe. And these PCIe are essentially called out the number of lanes from the CPU. So each of these SSDs, actually NVMe SSDs, actually require 4 PCIe lanes. Okay. The fundamental problem with this stuff, when you require 4 PCIe lanes, is let's take a simple example of a CPU. Look at a Xeon today, a high-end Xeon. It can totally support around 40 to 48 lanes. Now, if you divide the CPU lanes into ingress and egress, that means the front side and the back side, the front side is used up by the networking, because you're disaggregated. Somebody has to send data to the storage device, so that's through the network. And each of these network devices actually could require up to 8 lanes. So just off the bat, 16 lanes are just taken just for the networking. And then you have remaining, 24 lanes or so. And this is assuming there are no other peripherals, by the way. If you have peripherals, another 8 to 16 is gone for that. So this basically says, at the most, a CPU cannot drive more than 6 NVMe drives. So there are lots of people who actually put 24 drives with a single CPU, and you should ask the question, how the hell is this possible? Especially when you're building a storage array and you want to have lots and lots of drives, NVMe drives, let's assume, all NVMe flash array or whatever they want to call it. How many CPUs would you need? So what this basically says is dual controller architectures are fundamentally a problem. These are okay when those drives were slow, when the drives were run using mechanical disks. These were okay when the protocol was slow, when even though flash was fast, you never could exploit it. But we are in an era where there's NVMe Express. With NVMe Express and NVMe drives, you're actually giving full bandwidth availability. The networks can now talk to it at full bandwidth. The drives can now, consume data and serve data at full bandwidth. But the problem here now starts becoming the CPU. So let's go a little further. So what this really means is, in this new era of really fast media, and storage class media is going to just make problems more difficult. Do we really need to rethink how storage subsystems are designed? Does storage subsystem design need to reboot? It's very simple. Like, for example, you have a car, and you have an engine that's just rated at 100 miles per hour. You have tires rated at 40 miles an hour. Just changing the tires is not going to make the car go at 200 miles an hour because it's bottlenecked by the engine. So we really believe, or at least I do believe, that storage systems just need to have a complete reboot. Because we are reaching an era where applications have to do more, they process more, there's a lot of data, there's a lot of parallelism, and the need for speed is there. And especially in rack scale design. And I'll touch up a little bit more on that as we go by. So we took a completely different approach and asked a very fundamental question. Why, if you go into a data center and say, what is the one class of device that can really ingress in a terabit per second and exit at egress a terabit per second at line rate? And those are not the storage devices. They're actually the networking devices. They figured out a way how to scale. If you want to learn how to scale, go talk to the networking guys. They know it. So we said, okay, let's look at how a network switch is really designed. So if you look at the network switch that is kind of a mock design on front, let's assume you have 20 input ports, 20 output ports, and they're interconnected through a fabric. And they're connected. These ports are laid out in terms of line cards, and each of these line cards have port processors and memory and all sorts of things, so they can really do fast switching inside, and they match ingress to egress speed and almost do it at cut-through speed. So what we did was, since we started ground up by looking at how a network switch is designed, we said, what happens if we just take the output ports and replace them with really fast SSDs? Are we going to now take a network-centric design for a storage system, wherein you have lots of line cards switching through a fabric inside, going out to SSD drives and through NVMe, PCIe, whatever it is? And can you get the performance as what the needs are going to be, today and tomorrow and going forward? And are they going to be able to keep up with the innovation that's happening in the media itself? And we were surprised. And we actually found that in spite of doing data management services, we can achieve amazing throughput, amazing latency characteristics. So having said that, we built the Pavilion Array. And it was a masterclass design in itself, because we had to keep many, many factors in mind. Because you can always build a system that is really fast, low latency, but we had to do it in a form factor that was inconspicuous in a rack scale design. So in essence, you can't have the storage just take up more than half the rack, because what good is that in a rack scale design if you don't have enough rack space for the servers? So the form factor has to be small. The other thing is we wanted to make sure there was enough density, right? Enough density in the sense we want to build a box such a way that you could grow inside the box all the way from, let's say 18 terabytes to like maybe a petabyte. So today you can get a one-use system, really dense systems. So this is not about just density alone, but if you look at the bigger picture across everything, it starts making a whole lot more sense, because you want to have the density, you want to have the form factor, plus you want to make sure that you did data management. When you start doing data management, the data touches the CPU. And when you touch the CPU starts becoming the bottleneck. So it's not about just putting more and more media inside a small form factor. It's also putting enough CPU inside the same form factor. Lots of CPU. And then we have to make sure that, cost is not unreasonable. It has to be affordable for people to the degree that pretty much costs the same price as a regular AFA, or even cheaper in many cases. Now, since we wanted to do data management, we want to make sure that when we deliver this product, it is not an operational nightmare, in the sense, go install agents on the host, go install volume managers on the host. None of these should really be a matter. So we decided to take the agentless approach, and our system currently is completely agentless. So if you're having a Linux box, one of the later versions of Linux, just plug in the 2 wires and you're done, good to go. The third thing is, since you're disaggregating at the rack scale, we want to make sure there was enough resiliency, because the blast radius has now become a little larger. So we had to make sure that it supported, things like everything was hot pluggable, it was non-disruptive upgrades were possible, complete HA every component. We had to make sure that we supported the equivalent of RAID inside that. So when you pull out drives, or drives go bad, nothing bad happens. Data is always available. And simplicity was very, very important for us. We wanted block storage to be as simple to use and consume as a typical NFS storage. So we did the whole thing using Ethernet. So to consume a block storage should be as simple as, mount storage from this IP address onto this particular device and be done with it. And finally, we want to make sure that this was not proprietary at all. We want to make sure everything was standard-based. Now, since we wanted to keep the cost down, we made sure that every component that we use inside our box was readily available from third party. So without any fancy ASICs or FPGAs, it was all commodity components. This was a real challenge, and we pulled it off. We actually delivered a box which was, 4U in size, which could have, 10 line cards in them, as you can see in this picture at the back, 10 line cards in them, and each one having, 4 100 gig ports. And redundant supervisors. These are a lot of terminology which you would typically see in the networking world. This is the first storage system in my mind which is completely agentless, does complete end-to-end NVMe over Fabric in a form factor that is consumable at a rack scale. I don't believe, but I could be wrong, I don't believe that there's anybody else who can do this. To top it all off, this beast out here can do up to 120 gigabytes per second of throughput at around 100 microsecond latency. And this is the top view of our storage box. As you can see, inside the 4U, you can have up to 72 NVMe drives. This means that doesn't mean you have to start with 72. You can start with as little as 18. You could go with 800 gig drives, NVMe drives, readily available. We use commodity NVMe drives. We've qualified quite a few vendors. So this is not proprietary flash or anything like that. You could just use any NVMe drive inside, standards compliant NVMe drive inside. And there are 10 line cards and 2 supervisors. And each of these line cards have 2 controllers. So these are dual controller line cards. And they can all see all the drives, and we had to do real software innovation inside to build pretty much a cluster file system that can work at NVMe speeds. That's precisely what we did. And every component here, redundant, the fabric is redundant, storage is redundant, the controllers are redundant. It's all using standards component, standard parts. x86, typical network merchant silicon, exactly what a switch would be made. So what we're trying to essentially do to build something at this kind of a scale, form factor, speed, data management, it's just like in the networking world. No matter how great servers can do, you still have to buy switches from the Ciscos and the Aristas. You can't do all software defined for everything. There's a place for everything. So we wanted to create a new breed of storage class subsystems using commodity parts that allow you to disaggregate the storage from every server inside a rack to the bottom of the rack. Now, one of the questions I keep getting is, why do you need so much speed? Right? So if you take a simple example of a rack and you assume there are 24 servers in a rack, and each server has, let's say, 2 to 3 NVMe drives, you just sum it up as to how much speed requirement you would need. There is not a single AFA today that can give you that kind of speed and consistent latency. So if speed performance was a baseline for us to make sure that we satisfy the needs of replacing locally attached NVMe drives with a disaggregator thing. So that we got done. And for that, we had to build this architecture. Second, we had to make sure we had all the data management features because the blast radius is a little bigger because it's a whole rack now. And this is now we're seeing customers actually interested in what we're doing and trying to come up with a design, especially because they went through the whole SKU consolidation process that I talked about before, and wondering how they can better utilize their flash rather than they being locked inside the server to how they can disaggregate it to the bottom of the rack and make this part of their standard architecture. Just as today you would have, when you design a rack, you would say, I got a TAR, I got a network switch on top. So we want to lead evolution, which is kind of like a revolution, to go towards a rack scale design where we say, in addition to just picking your TAR network switch, you need to pick your TAR storage for flash storage. And that's the big innovation that we want to bring to this field of IT. In essence, it's not enough if you just build hardware. We needed to build, really good software that exploited the hardware and keep the cost down too. Only then can you create something that has very low latency, extremely high bandwidth, at a cost that is affordable. In many cases, cheaper than the cheapest AFA out there, and save money for all of us, essentially. So I'll take questions now, if there are any.
Great, thank you, VR. We do have a few questions in the queue. I'll read those to you. The first question that came across is, why do you need this much performance?
Yeah, I kind of briefly addressed that. I mean, look, you take a single server. if you have two NVMe drives, and I pointed out around 800K of reads each NVMe drive can do. And there are people today looking at, 6 drives in every server. Sum it up, just one server would require up to 1 million IOPS. So if you had, 24 servers, that's 24 million IOPS right there. So I'm not saying you'll be using all 24 million IOPS. Now things are getting denser and denser. I know companies which are doing, 48 and 96 servers in a rack. And to satisfy the performance needs of all the 96 put together, you need a box that can really perform very well. That's why there's this need for speed.
Great, thank you, VR. The next question in the queue is, what kind of software do you have inside your box, and is any of it open source?
Yeah, so it's easy for I don't want to trivialize it. Nothing is easy in storage. You can actually take an existing open source software. Many companies have taken ZFS, modified it, and put them inside server boxes and call them a storage array with a bunch of disks, white boxed, and made a company out of that. We decided not to do that. We first said, what do we need from a hardware perspective to get this kind of performance out? We built that. Second, we said, what do we need from a software perspective that can use the hardware to deliver what the customer wants, what the environment wants? So we really had to build our data management layer, software, file system, volume manager, whatever you may want to call it, for NVMe drives, for the new switch-like design, to maximize the performance and minimize the latency guarantees that we give and to give consistent performance. So it was not easy, but it had to be done, and why not us?
Great, thank you. Next question is, do you see any monetary benefit other than saving on utilization when you use a disaggregated storage solution?
Yeah, so that's an excellent question. So one of the challenges here, if you look at typical depreciation cycles, the server depreciates, let's say, in 24 months. Intel throws out a new processor, people want to upgrade it, server keeps depreciating every 24 months. However, we're used to a model where storage actually depreciates 5 to 7 years. Now, by simply just clubbing server and storage together, essentially what you're saying is now your storage is starting to depreciate every 2 years. That's a colossal waste of money if you're going to be upgrading servers every 2 years. So you need to really go back, and I think that in itself would save a lot of money to the end user. Just separating it out, keeping them different, having different depreciation cycles, not locked in with Intel's processor refresh cycles even for storage. Why would you want to club this together?
Great, thank you. The next question is this product available today?
Yes, this product is available. We're doing POCs with quite a few customers, actually more than a dozen. And it is GA. So those of you who are interested, I would suggest just ping us back, and we would be more than happy to engage with you to see how this may fit in a rack scale design, or how it can just fit in a one-off application that can improve performance. But at the end of the day, there has to be a need. So if you're not doing rack scale, and if you don't need performance, and you stay where you are, that's what I would say. But if the need for speed, especially with all the AI, the analytics that's going on right now, I would be surprised that you don't need performance.
Great, thank you, VR. And that's all the time we have for questions today. So thank you everyone for joining us today. In just a few moments, you will be presented with a short survey on today's event. Please complete the survey to help us improve future events. Also, a recording of today's event will be sent out later today. We look forward to talking with you again soon, and have a great rest of your day.